Good evening, everybody. This is Mr. Steele. I'm going to work through, this is basically my trial run, my dress rehearsal of the first lesson for AP Calculus AB this year. I'm coming to you from the darkness of this study because it's really, really warm in my house for some reason. The AC doesn't seem to be affecting me here, so I'm just kind of playing it safe. As I did for Honors Precal earlier tonight, I'm going to go through, I'm going to use my clock to make sure that I can actually hold us to about 50 minutes here going through this first lesson. There's not too much stuff, like it's about the right amount of time, but the pace isn't going to be my natural pace. I like to go a little bit more carefully and slowly, so this is just me taking an opportunity to kind of practice it out. For the moment, let me point out that there is a question of the day, so obviously in class you'll be having the opportunity to answer this question of the day. I'm not sure this is going to be the format we stick with, but we'll see what happens. For the moment, again, I'm just throwing stuff at the wall as best I can and trying to kind of get my mind around some of the ideas of things that I'm trying out this year. So having said that, I'm going to pretend like right at this point we have finished the going over or talking about the question of the day, and we're ready to begin the actual lesson with 50 minutes to go. So on your mark, get set, coconut. So good morning, everyone. Thanks for being here. I'm glad to see you again. Hopefully you're able to make it in. In this video, or in this day's lesson, we're going to work through just kind of the basics of limits. And it's a concept that you've seen before, especially if you took Honors Pre-Cal here last year, but even if you didn't, you likely have. But if you haven't seen it before, it won't be a problem because we're starting from the ground and building up. Having said that, when I mention that word ground with regards to limits, that's absolutely true. Limits form the foundation of every one of the major concepts of calculus. So understanding limits will help you develop an understanding of what all these other techniques and tools we develop over the course of the year actually mean. So it's really important, even though it's probably the smallest portion of the entire AP exam, it's a hugely important topic in order to understand the concepts behind calculus. So as you'll notice on the page right now, as you look at the notes, I include a title as well as a number for the lesson so that you can keep things organized. The date's up there as well, so I encourage you to record that. This is kind of a general Cornell Notes format. It's based on the work that I did in Avid from, I think, 2011 to 2014. So feel free to use it if you find it helpful. We're not going to do the active stuff on the side. I'm just kind of letting you know. And then, yeah, with that said, our essential question, kind of our learning objective, says what is a limit? What are the most basic tools for evaluating them? And how can I think of them in the big picture? So we're going to attack that as well when we get there. I'll have to add something to my shirt, but we'll get there when the time comes. So without further ado, let's jump into the actual lesson. So to kick things off, where I want to start our discussion here is to talk not just about limits, but just in general, how is it that we're going to tackle this subject of calculus? It kind of gets its own thing. I mean, heck, if you think about it, like algebra, another fundamental concept of mathematics, calculus also has a pre-class that comes before it. Before algebra usually came pre-algebra. Before calculus comes pre-calculus. So in order to get in here, it's important to kind of establish the ways we're going to look at relationships. So we're going to be talking about change and area and all these different things, and the tool that we're going to use to do that are going to depend on the type of relationship we're given. So to kick things off, the first type of relationship we're going to see, or the approach we're going to take to calculus, is what I'm going to call the numeric approach. And if you're trying to figure out what it is that a numeric approach means, I would say that it's more or less like a table of values. So in other words, you're going to see limited data, you're going to see a few ordered pairs, and you're going to have to reason from there and draw some conclusions about the relationship in place. In other situations, though, we're not going to use a numeric approach because we'll have much more information than that. But we might not have our typical approaches mathematically. Instead, we'll be looking at a visualization of whatever the relationship is, which in this case is going to be a graphic approach. And that basically means that we're going to look at it visually. We're going to look at a sketch of a function. We're going to look at the behavior over the course of an extended interval of time. And we're going to look at and use that behavior to draw conclusions about the relationship. And then finally, the thing that most of us think about when we think about math, even though all of these things really do apply, would be what we often call an algebraic approach. And by the way, the one thing I'm learning in teaching in the dark here is I have a hard time identifying the camera. So I apologize for that if you're watching this video. As far as what algebraic approach looks like, it's kind of our traditional, it's a bunch of equations, it's literal expressions involving x and y. That will be our approach that we'll take. And oftentimes we will work with all three of these approaches with every concept that we run into, but typically people remember the algebraic approach and then the numeric and graphic doesn't necessarily stick. In this course, we're going to make sure all of them stick. Having said that, that leads us to the moment where we've been waiting for, which is to kind of kick off the actual calculus work we're going to do. And we're going to kick that off by defining the word limit. And now I'm going to let you know that this is not what someone would call a precise or technical rigorous definition of a limit. The rigorous definition of a limit is this. For every epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. So that's what's called the rigorous definition. I should have it written up there, but I'll see if I remember by tomorrow. That's not how we're going to approach it. That's a topic that oftentimes gets thrown into a Calc 1 class. As I mentioned in the intro yesterday, or today for me, we've set some of those topics aside to focus more time on topics that are more essential to the topic and more fun and more developmentally appropriate. So our definition of limit is going to be much less Greek letters filled. So the way we're going to define limit is as follows. And I'm going to just write it out because sometimes when I try to read while I'm writing, I kind of mess up. So I want to make sure I get this correct. Actually, I feel like my handwriting is kind of shaping up at this point. It's getting better. I feel like this definition should be already written to save a little time, but then again, this gives you time to actually write some stuff down, so it's probably better this way. Okay, so having said that, or having written this out, this is the definition that we're going to work from. I think it does a really nice job of kind of hitting all the important elements. In particular, in here it says that a limit is a description. So that first word is really key. Like in a sense, limit and description is what we mean by limit. So it's not quite the same thing as a literal value. Sometimes it will be. It will be the literal y value we see on a function. But other times it's not going to be an actual y value. It's going to be a description of the behavior of the function. And in fact, it doesn't just say the behavior, but it says general behavior. It doesn't say kernel behavior. It doesn't say lieutenant behavior. It says general behavior. So what I mean is we're not necessarily talking about, again, at a particular point. We're saying kind of in general. If we overgeneralize, if we make it a broad observation of what's happening, what is going on here. And then from there it says that it's a description of the general behavior of a function around a given x value. And as you read this, you might kind of get this feeling and kind of be like, this is really imprecise. Like, this is kind of awkward to describe these things. We're talking about general behavior and around and description. Like, these don't feel very rigorous. And you're absolutely right. They're not. That's what that other epsilon delta definition does, is it makes this a really rigorous and precise description. But we're not going to go that way. So instead, we're trying to build up your conceptual understanding of what it is we're talking about with a particular limit. So let's just kind of go with this one for now. So you're looking at this particular, we're looking at limit, and down right below it, I've drawn a function for us. The function here is g of x equals x squared plus 2x minus 3 over x squared plus 5x plus 6. So this is a rational function, I can tell because it's a ratio of two polynomials. And of course, this is just a function, there's no limit here. But we might be interested in, for instance, what is the limit as x approaches negative 3 of this function g of x? And if we were to approach this using the different approaches that we have, we might get different values. So for instance, one possibility here, and let's see if this works. One possibility is we could actually use a table of values, and we could approach it, we could approach it numerically. So let's throw this thing in here once. Minus 3, x squared plus 5x plus 6. Very hard to type in the dark. So at this moment, it's, oh, look at that, we got issues. Unfortunately, my table doesn't necessarily work in the same way. Let me see if I can do this. 3. I'll just not save this because this is for later in the lesson. Okay, 2. Oh no, see, this is what I learned from doing these practice runs. I learned not to make the same mistakes. No, sorry. All right, close enough. So basically what we've got here, ignoring this last part of the table, is if we look at this, we've got a table of values that describes for us numerically what's actually happening with this function. So it's telling us that as we examine the behavior around x equals negative 3, it appears, oh, I forgot something. Oh man, this is embarrassing. There we go, much better. So you can see on the graph on Desmos what it's doing is it's plotting all of these points as though we're trying to see where all the points are. But what these are doing is they're basically pointing us towards what's actually happening with the function as we approach the value -3. And you can see that there's something kind of wonky happening here. Like, look right there. It says that at -3, our function is undefined. So unfortunately, if we take this numeric approach, it might immediately scream out to you as though the numeric approach doesn't give us any information. But take a look a little bit closer. Like, stick with me really fast here. Let's see if I can do this. Move it over a little bit. If we look at this, look at the trend. As our x values get closer and closer to -3 in both directions, look at those y values over here. Like, what I notice is on the, let's see, on the right side it's going 4.03, 4.003, then it's undefined. And then from the other direction, we've got numbers like 3.997 and 3.9997. What it looks to me is that this information is implying to us that our limit, at least as we approach -3, is equal to 4. And again, we don't know for sure, so I can't write 4. I can say that it's 4-ish, it looks like, but we don't know for sure. But that's at least a good piece of information. So the numeric approach gave us some really fruitful stuff, at least. Likewise, we could also, this is going to be very disorganized, I apologize. We could also look at a graphic approach. So we could just look at the picture of the graph and see what it actually looks like. And we already have that ready. So I think if I turn off this function, we can zoom in around, let's see, -3. And look at that behavior. As we get closer and closer to -3, you can see that it's undefined right there, but look at how close that is. In fact, I bet if we put in the point -3, 4, it would almost look like it fit on the graph. And so basically what we're seeing here is that this tells us that graphically it looks like our limit is approaching 4 as well. And again, the question might be, is it actually 4? Is it like 4.027? Like, we can't really tell based on what we've seen so far. But at the very least, we're getting some good information out here. Like, we see once more that it looks like, in our situation, the limit is going to be equal to something really close to 4. Not perfect, but we're getting there. Last but not least, you might think, oh, let's go try the algebraic one. Like, let's throw something into an equation. So if we take the algebraic approach, the way we would do that would be to just kind of plug directly in. We'd see what happens if we plug -3 into this expression. The good news is it's very easy to plug into this expression. Like, look at how nice this is working. The bad news is what happens when you actually evaluate what comes out. Our numerator goes to 0. That's 9 minus, wait, that is, oh, I plugged in -2, I apologize. 9 minus 6 minus 3, which is 0. The denominator goes to 9 minus 15 plus 6, which is 0, which means the value of this limit is 0 over 0. And that's not a good thing. You cannot divide by 0, and you especially can't divide 0 by 0. So unfortunately, what this tells us is that we just don't have enough cowbell yet to be able to figure out what this limit's value is. But we've got a bunch of different approaches that at least 2 of the 3 are telling us that it looks like we're approaching 4. So obviously we will figure out and we will determine on Tuesday how it is that we can actually evaluate this and find out that it is indeed equal to 4. But for the moment, we want to think about limits in lots of different ways. So today's not just about finding that answer algebraically, it's about developing that conceptual understanding of what it means. Having said that, like, the notation for limit is really essential and really important that you're able to approach it. So let's go ahead and define, or like write it all out here. So what you can see right off the bat is what that statement of a limit looks like. And I think it's oftentimes helpful for someone to figure out how it is that you say this stuff. Let's see if I can do this right. So how is it that you say and read this expression? Because I've heard some pretty uncomfortable things being said here. The way you'd read this is the limit as x approaches c. And once again, I'm wishing I had already written it out, but we'll see. The limit as x approaches c of f of x equals L. And this is the absolutely proper way for you to state what this says here. It's not lim x arrow c, f parenthesis x parenthesis, sideways parallel lines L. That's not what we're going for. So this is the way we're going to do this. As far as the components, to kind of give you a, I want to call it like almost an anatomy of what's here. This c value tells you the x value. And in the best way I could describe this, I want to make sure my notes said it as well. Like, this is basically the neighborhood. This is where we're interested in what's actually happening. Like, which neighborhood are we trying to figure out what the general behavior is? And so this tells us. In this case, we're looking around that x value, x equals c. Not necessarily at c, but around c. Second, we have the function behavior. Is that how I call it? Yeah. So we'll call this the function itself, or the function that we're trying to analyze. It's the relationship whose behavior we're interested in this case. And this is, let's see how we call this. I mean, obviously, this is the value of the limit. Yeah, okay. I'm the one who wrote that down. But in a sense, this is the y value we're getting kind of close to. It's the y value that describes the general behavior. Okay, actually, I'm going to write it that way. I like that better. The y value that describes the general behavior. Ooh, I like that. I like that a lot more than the fact that the team I'm representing on this hat is already out of the bubble. Let's see, y value that describes general behavior. So in other words, we're trying to seek a description for that general behavior, and oftentimes it will indeed be a limit. So a good way to describe and kind of think of this process, let's see if I can delete that. There we go. Like, what we're trying to say when we're analyzing and discussing limits is we're trying to say something to this effect. As our x values get closer and closer to the value c, values of y equals f of x get closer and closer to L. And in fact, if you recall really briefly when I said that epsilon delta thing earlier, that's literally what that was saying. It was saying f of x and L are suitably close when x and c are suitably close. So it's establishing connection between closeness in x to closeness in y. And in fact, there are some pictures I could draw for it, but for the sake of time, I'm not going to. So at this moment, I'll pause for just a moment. I'd say that I'd probably want to ask if anyone has any questions at this point, but since there's no one here to ask me questions, I can't do that. So at least I'm able to kind of see where I'm at. Boy, okay, 16 minutes, but I think it was a good, well-spent 16 minutes. The question, though, at this point probably becomes, okay, then, how is it that we actually evaluate a limit? And so at this point, we're going to start looking at what it means to actually evaluate a limit. Like, how can we determine what the behavior is? And the truth is, when you go to evaluate a limit, like this particular one, and to demonstrate that proper mathematical jargon here, this would be read as the limit as x approaches 2 of the function 2x minus 1 is equal to what? We're trying to evaluate that particular limit. So we're interested in what's happening on the graph of y equals 2x minus 1 as we approach x equals 2. So think about this for a moment. The key question to ask yourself when evaluating limits is, does this function behave nicely? And not just in general, but like around that x value. So around x equals 2, does this function behave nicely? And the question I'd probably ask is, well, what type of function is this? Like, what function has the behavior y equals 2x minus 1? And you'd say, line! And you'd be right. Absolutely, y equals 2x minus 1 is indeed a line. So we're interested in the behavior of a line, and lines are really predictable. They grow the exact same way all the time. So in fact, we could graphically represent what this function looks like pretty nicely. It's 2x minus 1. It looks something like this. There's no holes, there's no asymptotes, there's no breaks, there's nothing bad that's happening here. We're in particular, though, interested in what's going on at x equals 2, which is somewhere over here, I want to say. But at this point, we don't really need to even go measure it algebraically. What we can do is we can just directly plug it in, because as long as the function is well behaved, the limit's value is equal to the function value. And in fact, that property is called continuity, which we'll define next week as well. So what we could do is precisely this. Take our expression, plug it in, and in this case, we'd get 4 minus 1 is equal to 3. So now our answer for our limit, the first official limit we've evaluated completely 100% in Calculus AB, the answer is 3. By the way, I'll mention this later, but on AP Calculus exam, as well as in this class, you don't have to actually simplify anything. So, and a correct answer would have also been 2 times 2 minus 1. So that would also have been correct. So if you decided not to stop, or you weren't sure what 2 times 2 minus 1 is equal to, you could get away with it. So what you're seeing here is our first limit evaluation technique. And in particular, it's kind of our first algebraic limit evaluation technique. And it all relies on that question, does the function behave well in that area? So if there's no awkward or difficult behavior to handle in that neighborhood, we can just evaluate it by this technique that, once again, I called direct substitution. And it's direct substitution because you just go directly to the function and you substitute in that exact precise x value. So we're going to use direct substitution here first as an algebraic technique. Obviously, there's more difficult techniques out there. We're starting straightforward. So looking at this first limit, we're doing the limit as x approaches 0 of x squared plus 3x minus 1. A good place to start before you evaluate it is to ask yourself, what does this look like? And looking at the fact that this is a squared function, I'm thinking this is a parabola. I'm pretty sure it would be somewhere over here. I might be slightly off, but the important thing is parabolas are polynomials, and polynomials are continuous everywhere. Basically, there's no weird or awkward behavior that would cause a limit to be a problem. So we can go ahead and perform direct substitution. So here we go. We get 0 plus 0 minus 1 is negative 1. And we've evaluated a limit, and it was just plugging a number into a polynomial. So it works really nicely when our function behaves nicely. Likewise, when we get into our second example here, as you look at this rational expression for the first time and you kind of analyze what's there, you might look at this and go like, well, shoot, that's a rational expression. Like, oh, it's got a vertical asymptote. Like, there's something that makes the denominator equal to 0. And yeah, you are 100% right. There absolutely is. But our problem with this, or the issue here with just kind of assuming it's impossible and not doing it, is that the vertical asymptote, or maybe even a hole that's occurring here, might not actually be around the particular neighborhood we're looking at. So in this case, yes, there is some awkward, what we'll call discontinuous behavior, but because the x value we're interested in, the behavior around, does not correspond with the x value where there's a problem, we can evaluate this by direct substitution as well. So in this case, we can actually jump right in. I believe this is going to work out fine. Like typically what I do if I want to make sure I can jump right in is I check if the denominator goes to 0. If it doesn't, then I just plug directly in. But there are some exceptions to that. So from there, we'll be right here. Now keep in mind, as I said earlier, we don't need to simplify. So if you wanted to stop right there, you can be my guest. I mean, heck, you're going to be grading some of your own work as well, in addition to me later on in the term. So it's not the end of the world. This will be 1 minus 1 is 0 plus 3, so 3 over 5. And there is our limiting value once again. So that's saying that the y values on that function are getting closer and closer to 3/5 as x gets closer and closer to 1. Third, we've got one last limit here to use this direct substitution technique with. Probably shouldn't spend 3 minutes on it, but we'll play along for the moment. So in digging in right here, so we look at this limit as x approaches 7 to 42. Sometimes this kind of throws people. Like they're like, well, wait, where do I substitute it in? And they start doing some really funky stuff. They like, I don't know, turn it into a 7 right there. Like maybe this is a backward 7. Like, yeah, no, don't overthink it. In this case, let's imagine what the behavior of the function is actually doing. So if we think about it, y equals 42 is indeed a line, but in fact it's a line with horizontal slope. This is what we often call a constant function, because the y value is a single constant value over and over again. The way that shows up graphically is just a horizontal line. So no matter which y value we look at, and no matter which neighborhood for x we look at, we're always going to have the same y value. So in fact, for a constant function, the limit is equal to 42. So pretty straightforward. Direct substitution works really, really nicely. People tend to really enjoy direct substitution, although sometimes you get really into doing the more difficult techniques and you forget to even check the most important and simplest one. Now, having said that, these are all the pretty nice, yay, look at this, situations. But the truth is there are some bad situations that are out there. And actually, it's kind of interesting. Like one of the few little silver linings of doing the lesson this way is that well, no one's blocking your ability to see the bottom of the screen, so I can actually write down there. So bad situations that are going to pop up. There are actually a couple different ones that we're going to run into, and we'll focus on many of them in different cases throughout this term. But for the very beginning, a very straightforward bad situation that pops up is when you have a number divided by 0. So if you have a number divided by 0, this is telling us about something going towards infinity in all likelihood. There are some exceptions, but it's going to an infinite value, so it doesn't have a finite numeric value like we would want in this particular case. So that would be a bad situation, but it's something that we already kind of know what's going on. There are some situations, though, where we can see there's a problem, but we don't have a way to evaluate them just yet. The most common of those situations is the one we ran into on the first kind of general example, 0 over 0. You'll also have problems if you run into infinity over infinity. You'll run into problems with 0 to the infinity, infinity to the 0, oh yeah, and then this one, 1 to the infinity. All of those situations are problematic, and in fact, they all get a name. These guys are called indeterminate. And the reason that they're called indeterminate is you can't determine it. That was meant to be a joke, but it's also the truth. Basically, from looking at it, when you see 0 over 0, the answer could be 0. The answer could be 1. The answer could be 42. It could be 7/5. We don't know. We need to do something else in order to kind of peel back the onion and see what's on the inside. It's like if someone wraps you a birthday present of some kind, and you can't tell what's inside the box. So you unwrap it, and then you open it up, and you can see what's in the box. Same thing's true when you run into one of these situations. It's just not a super fun birthday present, if I'm calling it that way. From here, like of course, before we get too deeply into like the conceptual portion of limits, like we're doing okay on time, it's important to remember that limits can also be analyzed graphically in much simpler ways than pulling up Desmos and looking at a graph a little bit. So in this example, which hopefully I'll have the appendages printed for you if you'd like to print this graph to include in your notes, we're going to do kind of the pre-cal style attack on limits. So I've got a graph given to you of a function f of x. It's kind of weird and kind of funky. And we're going to go through and we're going to evaluate each of these limits. So in digging in here, let's start at the very beginning. It says the limit as x approaches -3 of f of x. So we're interested in what's happening to the function f, which again is this whole like weird thing, in the neighborhood of x equals -3. So looking at my graph, -3 is right here. So we're interested in what's happening with the y values as we approach there. Now you can probably look at this really fast and say, oh look, there's a dot there. It's at y equals -2. This limit is equal to -2. And you would be 100% right. But rather than kind of just look at it and kind of pull a dot off, I'd rather encourage you to think like this. As we approach it from this side and we approach it from this side, it looks like our y values are both getting closer to -2. So it's approaching y equals -2 in exactly the way that we need in order to describe what's here. So in general, the y values are getting closer to -2 as the x values get closer to -3. And in fact, that does evaluate our limit. So we would say the function is continuous in that area, so the limit and the function value are the same. Second, we've got, oh shoot, I've been writing on the template this whole time. Oh well, we'll figure it out. So in our second one, let's use a different color here. We'll use plum. We want to know what's happening, the limit as x approaches 0. So again, we don't want to just look at the dot. It's very tempting for someone to just say, oh, it's equal to 2. But it's actually not. So what I mean is this. We want to see what's happening in general. And in general means from every direction, like around x equals 0, what's going on? Well, as we approach from the left, it looks like our y values are getting closer and closer to 0. So one possibility here is that the limit's equal to 0. On the other hand, as we approach from the left side, or from the right side, the y values are getting closer and closer to 2. What that tells me is that we have inconsistent behavior. It's like doing something different depending on which way we look at it, from which direction we approach it. So the answer here is that the limit doesn't exist. Basically, we need consistent general behavior. Like otherwise, it's just not descriptive enough. You know, it's like if you were someone you were trying to describe to someone like your best traits, and you were interviewing for a job, and someone asked you like what kind of worker you are, and you said, oh, I'm the most diligent worker in the world. I care about my work. I work hard all the time. I stay late. I clean up after myself, except for the days when I go crazy and throw a party when the building closes down. Like that would be inconsistent behavior, and that wouldn't work out well. Like your job at that company would not exist. So such similar situation here as well. Like you need them to be pointing to the same place in order for the limit to exist. Our third little situation here, I'll switch to green. Let's try that. So the limit as x approaches 2 of f of x. Now, of course, I like to throw challenging kind of questions in there, but looking at this, the first most important thing to note is that there's no ordered pair at x equals 2. Like, I can't deny that. But the limit could still exist. Don't think just because there's no point there that the limit doesn't exist. In fact, looking at this guy, as we approach from the left and the right, we're getting closer and closer to whatever the y value is that's right there. So the limit does in fact exist. The problem is our question is, well, what is that limit? And the truth is, in order to approach it, we should point out that on the interval that we're interested in, looks like on the interval from 0 to 3, we can see that y is equal to, it looks like, let's see, y is equal to, let's see, slope. I'm thinking of the slope of the line here, by the way. I should have said that. Our slope is up 1 over 3, so it's 1/3 x, looks like plus 2. So having said that, that means that's what f of x is equal to. And by the way, this is kind of a lie. It's on that interval except for when x equals 2, but we'll set that aside for the moment. So that's our behavior. If we want to evaluate this limit, we'll plug it into 1/3 x plus 2. It looks like we've got 2/3 plus 6/3 is equal to 8/3. Also known as 2 2/3, and that does look pretty reasonable for what I see on the picture. So what I did was I wrote out what the equation of the line was for that segment, or most of that segment, and then I plugged in the value. We were trying to find what's called the hole at that point, and again, the limit existed because even though the point didn't exist right there, they were still pointing in the general direction of what was happening. It'd be like if Walmart was imploded, Let's see, I like the story about the multiverse. Let's say Walmart was zapped into a different dimension, and someone pointed out to like where's Walmart, or where was Walmart, like what's happening around Walmart, or whereabouts is Walmart. You'd still be able to describe where it was before. There'd just be a giant hole there. Like that's probably not a good situation for the infrastructure of Elk Grove, but hey, we can't have everything. See, this is what these rehearsals are for. I learned which jokes not to make, because that one just didn't land for me. Last but not least, I'll use red this time. We're interested in what's happening as x approaches 3, and I bet this is one that I could let you do really quickly. Take a look. Here's x equals 3. Like, I'll do this for the sake of nobody's here to help me. As we approach from the left, we approach y equals 3. As we approach from the right, we approach -1. This limit does not exist. It's going to 2 places. And 2 places might as well be no places, because you're gone. Like, there's no limit. The limit has to be consistent in both sides. So do you have any there's no one here. I was going to say, do you have any questions for me regarding what we just worked through, the visual approach to limits? But nobody's here. So we'll continue from there. Okay, so having said that, we just mentioned a graphical approach to limits. Sometimes, like, there may not be a graph provided, but you can still use a somewhat graphical approach to attack and evaluate a particular limit. So in this first particular case, we have the limit as x approaches 3 of 1 over x minus 3 squared. Now, if you evaluated directly, you'd see that the direct substitution yields 1 over 3 minus 3 squared, which is 1 over 0. So a correct answer here would indeed just be does not exist. This limit does not exist because it's not a finite value that it's approaching. And we didn't get one of those indeterminate 0 over 0s where we're just not sure what's happening. We got a straightforward 1 over 0. Something infinite's going on. But, having said that, if you sketched out this function, you'd actually be able to describe the behavior of this function a little bit better, in my opinion. So there's actually another answer that I would accept in this case. Looking at this thing, we can see that there's going to be a vertical asymptote at x equals 3. So again, this is all just kind of jogging your memory to some stuff you haven't seen for a while. So there's a vertical asymptote. Judging by the numerator being positive and the denominator being squared, this is always going to be positive. So in fact, the only way that this graph can behave is exactly like this. So we have, in this particular case, an anteater. There's a ton. So we have an anteater graph, or a volcano graph if you prefer. And the reason I bring this up is if someone asks me what's happening as we approach x equals 3, it's actually not hard to see. I'm going to use red for a moment. As we approach from the left side, the values keep getting bigger and bigger. From the right, we get bigger and bigger. So, having said that, I would also accept the description positive infinity as the value of this limit. It's not quite as precise, it's not quite perfect here, but it's a very strong and accurate description of what the general behavior of the function is in the neighborhood of x equals 3. It's what we'd say is growing without bound. So, and once again, all we did was sketch a graph of a function that we've seen before to get a really good idea of what's going on with this particular behavior. Likewise, we could also approach things, like, and again, okay, I should say this a little bit better. This first one was us taking a graphical approach. And again, we did kind of use a, a algebraic approach for a little bit, but a graphical approach was a nice way to do it. But this next one might not be one that you're comfortable doing a graphical approach with. I understand that a lot of people struggle with this particular problem. So instead, what I'm going to point out is that this might be a good approach to take a numeric one with, or this might be a good problem to take a numeric approach with. So what I mean is this, like, there's obviously an issue here. If you try to evaluate this and plug in 2, you'll get 0 over 0. And I'll talk about why I didn't write equals 0 over 0 on Tuesday. For now, just kind of take into account that we didn't want to write 0 over 0. So from here, I want to take a numeric approach because I just have a feeling I'll get some good information here. So what I'm going to do is I'm going to generate a quick table of values. I'm going to write x values on one side, and then I'll write values of x minus 2's absolute value over x minus 2. Now looking at this function, I can see really clearly that there's a problem happening at x equals 2. So I'm going to put x equals 2 in the middle of this. And then from there, I'm just going to kind of assume that if I plug in values that are slightly smaller or slightly bigger, that I'll be able to get a good view of what's actually happening with this function. Might not be perfect, but we'll see what happens. And obviously we have some sort of issue that's undefined at x equals 2. From here, if we plug in 3, we'll get the absolute value of 3 minus 1, or 3 minus 2 over 3 minus 2, which is equal to 1. If we plug in 4, we'll get 4 minus 2 absolute value over 4 minus 2, which is equal to 1. By the way, if we plugged in 5, 6, or 42, we'd get the same thing. Notice that the magnitude of the numerator and the magnitude of the denominator are completely the same. They're identical, which tells us that in this case, like basically we're always going to get 1 for those values. But on the other side, something else happens. If we plug in 1, we'll get the absolute value of 1 minus 2 over 1 minus 2, which is equal to negative 1. And if we plug in 0, we'll get 2 over negative 2, which is negative 1. And negative 1 similarly gives us negative 1. So what this picture is showing us, and I'll just kind of translate it graphically for us, what we're seeing is that at x equals 2, nothing's really happening. But for values larger than 2, it appears that all of the y values are approaching positive 1. Whereas for all the y values, or x values less than 2, it appears that our y values, excuse me, all of our y values are approaching negative 1. So in this case, at first it kind of throws you. There's a ton of stuff going on. But if we take a moment to evaluate this limit, like notice, once more, we have from the left side we're approaching negative 1. From the right, we're approaching positive 1. Negative 1 and positive 1 are different numbers. Same magnitude, but different numbers. That tells me that this limit also does not exist. It has inconsistent general behavior because it's going two separate places. And again, I know you've seen that before, so that shouldn't be much of a surprise. So there's kind of a numerical approach to everything. Keep in mind, though, that numerical approaches don't have to be limited to just like you doing it by hand. You could also take advantage of a graphing utility. So let's take a look at this particular limit. The limit as x approaches 0 of the sine of 8x over 2x. And once again, as you kind of copy it down, just to kind of verify that something's going on here, the numerator is sine of 0, which is equal to 0. I know trig's probably not off the top of your head. The denominator is 2 times 0, which is equal to 0. So this is what we call indeterminate. So we can't just use direct substitution. We need to approach this from a different direction. So what I'm going to do is I'm going to pull back in Desmos. So we have sine of 8x, and then we'll do 2x. Obviously, my table is now broken. And we're at 0. This is the most annoying part of this whole thing. Okay, so in looking at this expression, getting rid of that point for a second, we're interested in what's actually happening as we approach x equals 0 on this particular function. And it may not jump out at you immediately, but I can make this a little bit bigger for us to look at. But once again, think about this numerically. Like, look at the trends. As we approach from values that are less than 0, it appears that we're getting closer to like 3.999. As we approach from the other direction, we're getting values that also look like they're going to some value that's really close to 3.9999999. I think you can probably predict that this limit is going to be equal to 4. And in fact, that is the value, but the particular approach it would take to get there would require either what's called the squeeze theorem or L'Hopital's rule. So we'll learn those techniques later. We may put off the squeeze theorem for a while. We might not be able to squeeze it in, but know that there are possibilities out there. So again, your graphing calculator can absolutely help you through a situation like this as well, if the situation calls for it. And I think your problem set for tonight actually focuses on that first and foremost. Having said that, like oftentimes limits are interesting because they reveal some really valuable and interesting behavior, or they help us describe the behavior of a piecewise function. So to kick things off, this is something I've done every year in calculus. I want you to give me 3 animals. So we're going to talk about a piecewise function conceptually first by Frankensteining our way through this. So this is going to be animal of x. So give me 3 animals. Let's go a cat. Let's go a rhino. And let's go with a, I've drawn turtles already. Let's go with a fish. So what we're going to do here is we're going to define a piecewise function. We're going to say that it's going to be a rhino when x is equal to head. Let's say that it's going to be fish when x equals tail. And then for cat, oh, that's boring. Let's flip that. Let's say that fish is going to be x equals body. And then for cat, we're going to say x equals tail. So if you'll recall, a piecewise function is a way of taking a couple different function behaviors and bringing them together into a single relationship. It's saying that only for particular domains or values of x is there a particular behavior. And that makes sense, right? Oftentimes, one thing will behave one way at one moment, and then it'll change to another pattern later on. Like I think weather does that a lot, but lots of other things do as well. So now what we would look like, obviously we're not going to graph this in the traditional way, but what you could do is you can imagine this as telling us this is telling us what is happening on the function, and then the x values are telling us where that particular behavior, or in this case appearance, is actually going on. So with this particular one, it says that we have the body of a fish. So I think I can do this. Let's draw a fin. There we go, draw some gills on there. Yeah, this should work okay. We've got the body of a fish, and then it has the tail of a cat. So there's the tail of a cat, and then it has the head of a rhinoceros. I'm pretty sure they look like that. It's a horn. There we go. I've drawn our piecewise function itself, and we can see what our little animal actually looks like. It's not a very distinctive tail, but forgive me. Now the reason I bring that up is, of course, we're not going to be analyzing functions that look like that, although there are some pretty funny ones that are out there. Instead, we're going to be analyzing piecewise functions that describe more traditional algebraic behavior. So we might have a piecewise function that looks something like p of x equal to 4 when x is less than 0, and x squared when x is greater than or equal to 0. So that would be a representative piecewise function that we might look at. Now when we go to actually graph this function, what we're going to do is we, of course, are going to kind of look at where the boundaries are. And when I say boundary, I mean, like, where is the place where the two different behaviors start and stop. So I'd call this value x equals 0 the boundary. It's between the two different behaviors that are out there. And then what I'd do is I'd think about each one as being a separate portion. Oh, and it won't let me. Well, close enough. We'll play along for the moment. So I'd think about them as kind of giving me two separate values here. Can I fix this? No, I can't believe that. Okay, whatever. So it says in this first one that we're going to have the behavior y equals 4 when x is less than 0. So let's say that y equals 4 is right here. There's x less than 0, so I'll include an open dot because we're not including x equals 0. So there is the left branch, I often call them branches of the piecewise function, or the left arm of the piecewise. The other one is going to be y equals x squared when x is greater than or equal to 0. So we're getting the right half of a parabola. And we'll get that nice closed dot right in the very center, and this would be our piecewise function. This would demonstrate the behavior of this particular relationship. Who knows where it came from, but that is what the behavior would look like. Going on from here, though, these piecewise functions are ones you've dealt with a lot. You've run into them quite a bit in the past, particularly in pre-cal. I know this because I wrote the problem sets for your honors pre-cal, at least at Franklin. So you've seen these before. But there's a particular type of piecewise function that comes up a little bit more, and I think really is a good kind of closure point for the topic of limits. So we'll take a look at this particular function. F of x equals the function x squared minus 1 when x is not equal to 2, and x equals y equals negative 1 when x is equal to 2. So in trying to picture this, this can be a very counterintuitive one if you're trying to evaluate the limit. Because most people, and again, this may not be this isn't the right way, but most people go, oh, x does not equal 0. They kind of imagine that it's not there in their head. They go, cool, the limit's equal to negative 1. But unfortunately, that's not true. And the reason for that, a good way to kind of think about it, is to point out that there are lots of ways. There are lots of x values that are not equal to 2. Here are 3 of them. 42, 3, 2.11111. Like, all those are values that don't equal to 2. Whereas on the flip side, at x equals 2, there are very few. So what that means is if we're trying to describe the general behavior, and remember that's like saying like what's happening in general, like broadly speaking what's happening. Like that's asking us what's happening with most of the x values. What's happening in general here? So picture what this would actually look like. Basically, not to destroy this whole thing, but there's only one place where x is equal to 2, so let's just ignore it for a second. Everywhere else on this graph, y is equal to x squared minus 1. So we could quickly graph that particular parabola. The only difference would be when we reach that one point. Let's make sure I don't want to lose my color here. let's make sure. So the only place that it would be different would be like right here. So right there at 2, there's like a hole missing. It says the value would be -1. But everywhere else, we're looking at this parabola. And the reason that that comes up is now look what happens with our limit. As we approach from the left, we're getting close to the y value on the parabola. As we approach from the right, we're getting close to the y value on the parabola. So what that means is if you want to evaluate the limit as x approaches 2 of f of x, and I'm thinking that's what you want to do because that was the entire instruction of this particular problem. If you want to evaluate it, as strange as it is to say, you're going to use the part of the piecewise function that has x does not equal to 2. So in other words, you'll directly sub into the first part, and you'll get that the limit's value is equal to 3. Kind of weird, but thinking about this conceptually, what it means is we're looking at what's happening with a lot of different points. It doesn't really matter what's happening at x equals 2, it matters what's happening around it. Like we're talking about the general behavior of the function. So again, we don't focus and fixate on one single point. We look at the broad trends, and in broad trends, we are getting closer and closer to 2. Like in the neighborhood, there's we're getting closer and closer to 3. In the neighborhood of 2, there's a lot of 3ing going on, just maybe not at particularly x equals 2. Likewise, I'm not going to spend a lot of time on this one because I have one last thing to bring up here. Something I want to point out is that this last problem follows the same pattern. We've got some sort of weird relationship with a sine curve and a natural log. And once again, we've got the x is equal to 7 and x does not equal to 7. So there's this kind of lots of points versus 1 point mindset. If you want to evaluate this particular limit, the trick is simple. And it's not really a trick. I'd rather you think about it conceptually. We want to use all the points that are happening around 7, less than just what's happening there. But basically, we're once again going to choose the one that involves all the other points that are around there. So we'll directly substitute in because we're just trying to figure out what the trend is, like what's the behavior, not what's specifically happening at that one single point. And I have to think about this. ln 51, yes, okay. Whew, 7 squared plus 2, it's a rough day. So having said that, the last thing I want to kind of point out here is something that kind of throws people, is they see that the limit is equal to 3, but they're like, but that just doesn't make sense. And I think what's usually there is because there's this sort of awkward feeling because the function value is actually equal to -1. Or on this second one, the function value, I should have had g down there, that function value is equal to the sine of 20. So, messed it up. I'm feeling the clock, everyone. I'm really feeling the clock right now. So basically, like, there's the problem. These aren't our limit values. These are just the function values. So that's like describing this single point. But we don't care about a single point. We care about the general trends, like the general behavior of the function. So keep that difference in there. It's a little bit weird when you start off, but I think it'll really work out well. So now having said that, this last little bit is just kind of a takeaway that I want to throw in there. And to help me with that, I'm going to decorate my shirt really fast with some really old double stick tape, I think. So basically this question, as it says up there, asks you to kind of decide, like, if the limit as x approaches 2 of f of x is equal to 14, then f of x, or f of 2 equals 14. Is that true sometimes, always, or never? And in fact, I'm going to kind of spoil the surprise here. This is actually a situation that is, sometimes true. It's definitely not always true. And in fact, if this was phrased as a true or false question, if we asked the exact same thing with true or false, then what we would say is the answer is false, because you can find a counterexample that proves it's not true. And what this is really probing at is the idea of 1 point versus general behavior. And the way that I usually hammer this home, or that I'm going to attempt to hammer it home here really fast in the dark, is that I'm going to turn on the light really fast. And I'm going to stand here for a second. I'm going to ask you to regard what color my shirt is. And I'm hoping that as you look at it, you'd say that my shirt is black. The reason being that this is an overwhelmingly black shirt. Like, holy shoot, this is crazy. It's such a black shirt. It's totally a black shirt. It's a solid black shirt, especially now that I moved that over. That was why I was spinning around. So you're looking at a black shirt. But here's the thing. There's a white dot on this shirt. And sometimes people get really obsessed with that white dot. Like, you just fixate on some small little thing, and you don't see, it's an old saying, you don't see the forest for the trees. Like, basically, like, this one dot is just a single little white dot. Like, it's just one little point. just one little point. But if I ask you what color is this shirt, this is an overwhelmingly black shirt. So in fact, you don't let that one little white dot spoil the color. Don't let it change what the general perception is of the shirt. This is a black shirt with a single white dot, and that's the same thing true of a limit. Just because there's a single point that's somewhere out of place doesn't mean that the general behavior can't be calculated using some particular relationship. And kind of wrapping that up, I don't think this last bit was as organized as I wanted it to be, but there's a good way to kind of imagine this situation that's being described here, the difference between these two. Like, there are a couple different ways that this can go down. Oops. Let's see. There we go. Copy, copy. So imagine we've got a nice little relationship here. I've got 1 minute left. Oh my goodness. So we've got a situation in this particular case, if this is our function f of x, we've got a situation where at x equals 2, we're at the y value of 14. In this case, the limit as x approaches 2 of f of x is equal to f of 2, which is 14. But keep in mind, there are other situations that would be possible. It could be possible that we have this situation. So once again, this is f of x. Ideally, they'd be the same thing. 14 would be right there. 2 would be right there. But we have some other point right up here. In this particular case, the limit as x approaches 2 of f of x equals 14 again, because the y values that we're getting closer and closer to as x approaches 2 are equal to 14. But unfortunately, that doesn't equal f of 2, which is some other number. Maybe this would be the point 2 comma 50, in which case, like, those two are just not the same. So one doesn't imply the other. All it does is describe the general behavior or the specific behavior of the function. So having said all that, there's probably no chance that I can finish all of this tomorrow. So I'm going to make a small little cut somewhere. But in any event, that does complete the lecture portion of what's here. Obviously moving pretty quickly, trying to get some conceptual stuff into your mind. And to wrap things up, I do have a quick try it problem available for you. So you could access that try it during the extra time. Again, I'm talking to myself rehearsing. You could access that thing during the time, although I'm going to change that QR code, so ignore that for the moment. But basically, here's some quick practice problems. This lets you input your answers and check if they're correct, so you don't have to report back, but I'm happy to answer any questions. And then the answers will be on the next page in the notes that will be posted in the Google Classroom. So having said that, thank you for watching. Hopefully this was a good bit of exposure to get you the information you need. And until the actual class when I'll actually see people, thanks for watching, and have a great night.